Derivation of elastic potential energy. If you have a spring with the length L and you extend or stretch the spring to a distance with the extension X, the force applied in extending the spring, that force is directly proportional to the extension. What that meant is the higher the force, the longer the extension, and the smaller the force, the smaller the extension. This is a proportionality statement, a direct proportionality. Now I can change the proportionality symbol into the proportionality equation where F equals to Kx, where K is proportionality constant and X is the extension. This is similar to Y equals mx plus C, where C equals to 0. Y is F and M is your K. And because this is Y equals mx, if we plot F against the extension in meters and F is in newtons, we get a straight line through the origin. And the gradient of the straight line, when we pick 2 points on the curve, and we can find the gradient of that straight line, and that gradient is equal to K. To work out the energy stored in the spring when extended, that energy will be the force times distance. The force times distance will be the area under the curve. But this area is half of the rectangle, because if you do force times distance, you're finding the area of the rectangle. But we only need the half of the area. So the area is a half base times height. And so we can say that the area, which is the work done, will be equal to force times the extension divided by 2, and that will be equal to a half Fx. But we know what the force is. Force is equal to Kx. So what we can do is to substitute that force, which is equal to Kx, into there. And finally, we can get the work done for the energy of elastic potential energy equals to a half Kx times x. And that equals to a half Kx squared. And that's the derivation of the elastic potential energy.